Hello students, in this video lecture we will discuss the image position and lateral magnification produced by an optical system. In the previous lecture I have told you what is optical system. Optical system is simply a combination of refracting surfaces and lateral magnification. Lateral magnification is represented by m, which is ratio of y2 and y1. Now see what is y1 and y2. Y1 is the height of the object point from the optical axis, and y2, this is the height of the image point from the optical axis. And in image position we will establish a relation between the object distance d1 and the image distance d2. Okay, so here we will make use of three matrices to establish a relation between the optical coordinate of image point and the object point. Okay, so here you see from point O dash to P there is translation. So the coordinate of P point and O dash point, these will be connected by a translation matrix in the object space, which is given by this matrix 1 0 minus d1 by mu1, and d1 is taken negative because here the distances are measured from the pole of the refracting surface. Okay, and here the measurement will be opposite to the direction of propagation of the light, so this is taken negative here. Okay, then in between these two surfaces S1 and S2 we are considering optical system is there. So whatever happen in between these two surfaces, that is given by a system matrix whose elements are minus a, b, c and minus t. This is also a 2 cross 2 matrix, and this is combination of various translation and refraction matrices. And let from the system the ray of light emerge from point Q, and between point Q and I there is again translation. So we will make use of these three matrices to connect the optical coordinates of image point and object point. So if we write the optical coordinates in matrix form, then let us start from here. The coordinate of point P and O dash. So I am writing here O dash to P. There is translation. There is translation. So we will write a 2 cross 2 matrix which will connect. We will write a 2 cross 2 translation matrix which will connect the optical coordinate of P point and O dash point. So the optical coordinates of P point are lambda dash and y dash. So this will be equal to a 2 cross 2 matrix, translation matrix, which is given by this, and that is 1 0 minus d1 by refractive index of this object space. Okay, and then we have 1, and then we have optical coordinates of the object point, that is lambda 1 and y1. Okay, and now we will connect the optical coordinates of Q point and P point. So in between P and Q point there will be a system matrix which is given by this matrix. Okay, so here in between Q to P there will be a system matrix which is combination of translation and reflection matrices. So here we will write the coordinate of Q point, optical coordinate of Q point, which are lambda double dash and y double dash. These can be obtained using a system matrix which is A, B, C and D, and we will take A and D negative for our convenience of calculation, and then we have optical coordinates of P point, that is lambda dash and y dash. Okay, done. Now from Q to I dash there is again translation. Okay, and if we assume that if we assume that the image and the object, these are in the same medium. Okay, so here, so class, here if we assume that the object and the image, these are formed in the same medium, then you have to take this to be 1. Okay, so this is the thing which you will make use here, and then now we will connect the optical coordinate of I dash and Q. So here in between I dash and Q there is again translation. So here we will make use of translation matrix, and again it will be a 2 cross 2 matrix, and the coordinate of image point, that is lambda 2 and y2, these are connected with the coordinate of Q through a translation matrix, and that is 1 0, and here d2 is positive, and then refractive index of this medium which is taken mu1. Okay, so here we have assumed that this system is having refractive index mu2. That's why we are writing here mu1 and mu2. We are differentiating it. So if this system is placed, this optical system is placed in air medium, let we consider this to be air medium, then the refractive index of this mu1, this will be equal to mu1 will be equal to 1, because it is placed in the air medium, and then it will be replaced by mu, and then the refractive index of this space will also be equal to mu1 will be equal to 1 if this medium is to be air. Okay, and here the translation matrix, let us complete this equation, and here we will write the coordinate of point Q, that is lambda double dash and y double dash. Okay, so if we connect the coordinates of optical coordinate of object point and that of image point, then we have to put the value of y double dash, lambda double dash, y double dash from here, and then lambda dash and y dash from here, and we will make a combined matrix. Okay, so class, for simplicity we will assume that this optical system is placed in the air medium, so we will replace mu1 by 1. Okay, so if we replace mu1 by 1, then you will get this relation. Okay, and now we are to connect coordinate of image point, which are lambda 2 and y2. This is connected to the coordinate of Q via a translation matrix, and right here the matrix for translation 1 0, and then the translation is d2, and the refractive index, that is of air medium, which is 1. So here you will write 1, and then you have coordinates lambda double dash, y double dash, and for this matrix you can write this one. So here we will write then minus a, b, c and minus d, and then you see here you have lambda dash and y dash, and in place of lambda dash y dash you will write this one. Okay, and here you can see translation, system, translation. So if you write translation matrix here, then you can write this is 1 0 minus d1 by refractive index of here, that is 1. Okay, and then you have 1, and then coordinates of object point, that is lambda 1 and y1. So basically, to connect the optical coordinates of image and object, you are to multiply these three matrices. I am writing the result directly. You can do yourself. Okay class. Now you see, if you multiply these three matrices, then you will get this resultant matrix. So here you have minus A, and this is the 2 cross 2 element, that is minus A D2 plus C, and this is 1 cross 3 1 cross 2 2 cross 1. Okay, second row and first column. So this is 2 cross 1 element. Okay, so now, and here you have lambda 1 and y1. Now we are to find magnification, lateral magnification, which is given by y2 by y1. Okay, so for this we will multiply this, and the y2 will be equal to this element into lambda 1, that is b d2 minus d plus a d1 into d2 minus c d1 divide into lambda 1, and then this into y1. So I am writing it here, minus plus plus, I am taking minus inside the bracket, minus a d2 and then plus c into y1. Okay, so this is how you can connect y2 and y1. Now if this equation is to come true, then we will generalize this matrix. Okay, and for that, if we take the point O dash on the optic axis, mean to say we will consider y2 y1 equal to 0, then in that case the image will be formed at this point, mean to say y2 must be equal to 0. Okay, so this will be the case of the axial object. So here I am writing, in case of axial object, mean to say when the object is placed at the optical axis, then y1 will be equal to y2 and this will be equal to 0. So in that case, this relation between d1 and d2, or the coefficient of lambda 1, that has to be equal to 0. So for this particular case, this has to be equal to 0, or I will write b d2 minus small d plus a d1 and d2 minus c d1, this has to be equal to 0. So from here you can for this particular position of the object, you can establish the relation between d1 and d2, and d1 and d2 are the position of image and object with respect to refracting surfaces. So one of the tasks we have solved here, we have calculated the relation between the image position and object position. Now we are to find a general matrix, and the general matrix can be obtained by putting this element equal to 0. So the general matrix will be equal to lambda 2 y2. This will be equal to, this is b plus a d1, and then you have minus a is here, and then you have this is equal to 0, and then you have minus of a d2 and plus c, and then you have lambda 1 and y1. Okay, now we have reduced the optical system matrix to this matrix. Okay, now we are to find the lateral magnification, which is y2 and ratio of y2 and y1. So let me clear the surface. So here you see, we have, from this matrix we will establish the relation between y2 and y1, and from here you will get y2, this is equal to minus a d2 minus a d2 plus c, d2 plus c. Let me take it inside the bracket, and then you have y1. Okay, and from here we are to find what? Magnification, that is the ratio of y2 and y1. So from here you can write the magnification is y2 by y1, and this will be equal to minus of a d2 plus c. Okay, so this is the thing. And for this system matrix, we know that determinant of system matrix is equal to unity. So if we take idea from that, so here I am writing the system matrix which is in this case is b plus a d1, b plus a d1 minus a, okay, and then we have 0 and minus a d2 and plus c, and this is the system matrix. So if you find its determinant, then this will be the, from here you will find that of system matrix that will be equal to b plus a d1 into minus of a d2 plus c. This will be equal to 1 because this factor is 0. Okay, so from here and if we see in this relation, this factor is equal to the magnification, so we can write this is what? Magnification. Okay, so if we substitute the value of magnification, then I can write b plus a d1 into magnification, this is equal to unity, and from here we can conclude that magnification is inverse of b plus a d1. Okay, so this is how you can find the relation between the object distance and image distance and the magnification. So magnification is this one, okay, and you can write it again, magnification is this one. So this is 1 by b plus a d1. Okay, so here you can see how to find magnification, and if you put the value of magnification in the system matrix, then it will change. Let me write it again. Okay, this is the matrix, this was the matrix, and this can be written as, now you see what is this, b plus a d1, b plus a d1, this is inverse of magnification. So I can write here 1 by m magnification, then I have minus a, okay, and then I have 0, and here this factor, this element represent magnification, so I can write it m. So this is how you can write the system matrix. Thanks for watching the lecture.